today I'm going to talk to you about this programming language called Flix that we're building here at Aarhus University, also in collaboration with researchers from Canada, Germany, and other places. So just a brief outline. We'll be talking today a lot about effect systems. But maybe first I ask, how many here have written a program in a programming language that has a type system? If you could just raise your hand. Okay, so that's perhaps not surprising, most of you, all of you. But how many has written a program in a programming language that has an effect system? Raise your hand. Half a hand. Okay, cool. So that's what we're going to talk about today. And so I think, I don't know if you will all be Flix programmers in 10 years, but I think at least some of you will be writing programs in languages that have effect systems. And that's the focus of today. So first we'll see what is an effect system. Then we'll talk about how effect systems can be used to reason about mutable memory. Then we'll see an example of how such an effect system looks like in practice. We'll apply to, well, how do you write an iterator? Finally, we'll see something about how we can benefit from these effect systems with something we call purity reflection. And lastly, just sort of to tease the language we've been building, I'll show you a lot of the tooling we also have. Part of the message being that you can actually start playing with Flix today, start using it if you want. If there's one thing you should remember from this talk, though, that is that in Flix, it's a functional language at its core. So that means that you write programs by writing functions. And what is a function? It's something that maps an input to an output. Now, what makes Flix special, you could say, is that it allows you to write functions in 3 different ways. You can pick the style, if you want, that fits you the best. So for example, you can write a function in a functional way, so with some algebraic data types, pattern matching, these kinds of things, if you're familiar with that. You can write it in imperative style, so with loops, mutable memory, these kinds of things. And you can write it declaratively, so you can actually write a function as a small logic program. And you can choose between each of these styles. So if you're implementing a function, this style is the one that's most appropriate for this specific problem you're solving. And of course, the user of your function or your functions, well, they don't know how you've implemented it. So the style you choose doesn't affect them. They just see, oh, this is a function that takes a string and returns an integer, for example. So this is the one thing to remember. So we're trying to have a functional language, but you choose the style inside each function. Okay, now today I'll focus on the imperative style. So we're writing functions, but inside we want to use imperative programming as we're used to. Okay, now first, let's talk about the Flix effect system. So what is an effect system? Well, a type system, that's something that describes the values in your program, right? So you have strings and integers. And in most languages, if you know a variable has a type string, well, then that's a guarantee that you can depend on. It won't suddenly turn out that it's an integer at runtime. And you also use types you can use types to define. You can define your own types. For example, if you have classes, you can define a class for students, a class for persons, and so on. So type systems characterize values. Effect systems, perhaps not surprising, they characterize the computational effects of running a program. So for example, how does this program mutate memory? How does it interact with the outside world, if it does? These kinds of things. Now what's special about the type and effect system in Flix is that we have a strong focus on type inference. So that means that in principle, you don't have to write any types. The compiler will figure it out. And the compiler will only give you an error if there is actually a type error, something actually wrong with your program. Now that said, of course, we do like to write some type signatures, and today I'll show you lots of functions with some signatures on it. But I'm just saying the compiler will not force you to do extra labor to convince it that something is correct. Now the Flix type and effect system cares about 3 things, essentially. It cares about pure functions, so things that have no side effects. Then it cares about impure things, so for example, mutating memory, deleting a file, these kinds of things. And finally, a new thing we'll see today is something called effect polymorphism. So this is the idea that whether a piece of code has side effects or not could depend on another piece of code. Okay, you say, okay, that's all fine, but why should I care about this? Why do I even care about this? Well, if we track purity, so we know which part of the program are pure, then it allows us to understand the program better, both us as programmers and the compiler trying to optimize the program. So for example, I talked about how type system gives certain guarantees, and the same way effect systems gives guarantees. For example, if a function has no side effects, well then you know that the output is uniquely determined by the input. We also use it inside the compiler, so that's not something you see, but our compiler knows that if an expression is pure, then it can more easily move it around, duplicate it, eliminate it, run it in parallel without changing the meaning of your program. Now, without an effect system, you can still do such optimizations, but it's much harder, and often, well, you don't know if you can apply an optimization, so you have to say, oh, I don't do it. I'm not sure if I can do it. Finally, a point I'll get to towards the end is that by having information about these effects, we can empower library authors to write richer libraries. So for example, if you're writing a library, some data structure library, well, if you know that some function that's coming in is pure, then maybe you know you can run it in parallel and you might benefit. Now today that's really hard because if two pieces of code are interacting, well, you don't know if this has side effects on something maybe in the heap. You can't run it in parallel. Then there could be race conditions or deadlocks, all these kinds of problems. So these are the kinds of things an effect system enables. Okay, so now let's look at some code and see how it looks in practice. And I mean, this is a programming talk, right? So if you have any questions also during, just raise your hand and complain or ask. Okay, so here in Flix we have the add function. It takes two integers and it returns an integer, and there's some implementation here. And so what we can say in Flix is that the add function has no side effects. So there we have this backslash, and then we have the empty set of effects. So this means that nothing in here can happen that affects the environment. It's not going to delete a file, anything like that. It's just a pure computation. Now in this case, this was what the function does itself. We can also have a function like count. So what does count do? It's a little bit more complicated. Well, fundamentally we have some list L, some elements A, and then we want to pass in a function and want to count how many how many elements satisfy this function, this predicate. So for example, you have a list of students, right? And you want to count, well, how many students have a passing grade? So if we were to write this, where we've explicitly written the empty effect set here, that means that the function that's passed to count should be pure. It's not allowed to have any side effects. So that's something we can enforce if we want. And then in this case, we also say, okay, count itself doesn't have a side effect. Now, well, what if you do want to have a side effect? We can do that too. So here I have a function say hello. We get a name. It's a string, and we're going to say hello to that person. Now, printing to the console is the simplest side effect you can imagine. It's just going to make some text show up, right? But if we want to do this, well, we have to put in the signature that I'm actually using I/O. So you're saying, actually, I'm going to affect the environment. And so that means everywhere say hello is now used. You know, in your editor, for example, you have VS Code plugin, you can see, oh, here's a side effect. It also means the compiler knows that if there are some calls to say hello, I can't just swap them because their order is probably important. Aha, okay, so what if you try to cheat? So for example, what if you were to say, oh, I'm going to print, and I'm going to say it's pure. I'm printing and it's pure. Well, that's not allowed. That is a type error, similar to assigning an integer to a string and so on. So here we're told, well, an impure function has been declared as pure. This is not allowed. The system gives us a guarantee, just as a type system. Okay, so far so good. Now, where it gets a little bit more complicated is that if you've written some Java programming with streams, or maybe you're writing JavaScript, and you have higher order functions, we saw count, for example. Another example could be map. Then if we think about the map function, what does it do? Well, I have a list of A's, and I'm going to convert it to a list of B's. So again, imagine I have a list of students, and I'm going to convert it to a list of grades by picking out or computing the grade for each student. That's what you typically use the map function for. But now, if you call map, well, is that going to be pure or impure? That depends on the argument, because if you call map the pure function, the whole thing will be pure. If you call it with an impure thing, the whole thing will be impure. So this is what we call, a fancy word, effect polymorphism. could also say it's effect generic, would perhaps be another way to say it. And so here we're really just expressing that if the function f has the effect ef, then the whole map function here has the effect ef. To make it a bit more concrete, if I have some list and I map the function, I'm multiplying x by itself and adding 42, well, this function is pure, so this whole thing here will be pure. On the other hand, if I for some reason map the print function, I'm printing every element, well, then the whole expression will be impure. So this is a very important property to have in any language, I would argue, that has an effect system, because we often write code that's generic in whether or not it has an effect. Whether it has an effect depends on something else. And so that's something that's important to capture, and we can capture that. We can also use the effect system to catch some simple bugs. Here's a function, and well, what are we supposed to do? We check permission for something. Maybe there is some check permission function, and if that goes well, whatever that means, then we print access granted, right? Now, I haven't shown you the definition of a check permission, but actually it returns a Boolean that you're supposed to use. And so what Flix will say here is that this is a useless expression because check permission is pure, it has no side effects, doesn't interact with the environment. So writing it here, just calling it and throwing the result away, is never sensible. Now this goes a bit beyond what you can see in, there are some linters for Java and JavaScript and so on, where they talk about, oh, this return type must be used. And that's fine, and that's also important. But this here can talk about essentially having expressions or statements in your program that do not have any effect. And so it gives you more warnings if you've written something that's meaningless. And I think this is especially important when you are using libraries, for example, that you haven't designed yourself, because you might not be sure exactly about the API. And so this is much more aggressive at saying, no, this code doesn't do anything. Okay, so that was a very brief introduction to effect systems. We saw that we can capture when functions are pure, when they're impure. And here by impure, I really mean any kind of side effect. Deleting a file, talking to the network, mutating a state, and so on. And finally, we saw that it was important to have effect polymorphism. This function can be effect generic. One place where we already use this in Flix is that when you implement, for example, equals and hash code, these kinds of functions compared to string, then we force those functions to be pure. And this is actually important because there's been several mistakes in other languages about what can equals actually do. So does anyone know what the equals function on a Java net URL does? One or two URL objects equal in Java? So actually, if you give it two URL objects in Java, google.com and something else, it has to resolve them to an IP address, right? So actually, it goes on the internet and it looks up, what IP address does it resolve to, and if they're the same, then the objects are the same. That means you can have a set, right, like a hash set in Java with some URL objects in it, and if you don't have access to the network, and you try to put in an element, then it goes wrong. Now, this is, of course, a horrible design, and in the Java bug tracker, right, there is a 15-year-old bug, 18-year-old bug saying, this is insane, right? And everyone is like, this is completely insane, but it's too late to change it, right? But even if it hadn't been like that, right, nothing really ensures that you write meaningful equals and equal functions and hash functions. But in Flix, we force them to be pure. And that means we can actually trust that when they're used to implement a hash set or things like this, that elements, you can find them again, right? You don't end up with this situation where you put things into a map and later you can't pull it out because something has changed in the heap. Some of you will have seen these bugs and will know the pain. Okay, so that's one way we use the effect system. All right, so now I'll talk a bit about a region-based memory. But maybe first, to motivate this, I'll ask how many have programmed sort of with asynchrony or with futures or these things? If you could just raise your hand. Okay, so many of you have. So the first time you were exposed to this, or at least I was, it's like, okay, I get a future back, and now I want to, I want to get the thing out, right? But then, oh no, you map over it and you start writing this asynchronous style, right? So futures have this problem that they proliferate through the program, right? As soon as something becomes asynchronous, it goes everywhere, right? I mean, there are things you can do, right? But sort of in the simple model, it goes everywhere. Now we have the same problem here with impurity, because I just said that if you mutate memory, so if you allocate an array and you mutate it, then you're impure. That means if you call that function, then the caller is impure, exactly like in the future scenario. And those callers are impure. So now suddenly your entire program is marked as impure with the IO effect. So then you haven't gained anything, really. It's just become a huge mess. But really, if you think about it, what we often want to do is that I'm writing a small function, and inside I'd like to do some imperative programming. I want to allocate some data structures, like some arrays, some hash maps, whatever. And I'm going to do some computation on them, and then at some point I'm done, and I'm going to return the result. But by the time I return the result, those mutable data structures could no longer be in use. They can be deallocated. And that actually means that seen from the outside, my function is pure. It's just inside, I'm allowed to use some mutable state. And so this is what I mean by region-based memory. So the idea here is that we will give you a mechanism where you can say, okay, now I'm going to write in an imperative style, and you get like a lexical block, and in there you can allocate your mutable memory, you can work on it, and then at the end you return some result. The mutable memory is thrown away. The type and effect system checks that's the case, and then you're actually allowed to be pure. Now I think an example will demonstrate this much better. So let's say we wanted to sort a list. So if I'm giving a list here, it's an immutable linked list of students or something. Maybe I want to sort it by, I don't know, again, their grades. Now, sorting a linked list is not a good idea. What you want when you sort things, if you talk to algorithm people, is you want to put it in an array, and then you want to use like quick sort or merge sort or something like this, which is a very imperative algorithm. You're shuffling elements around. This is the fast way to do it. This is the right way to do it. But luckily, we can actually express this idea. So there's this new construct called region, and it says, okay, I'm introducing a region here. So that is permission to do some imperative programming inside this block. And I get a region capability here. And I use that to say, okay, take this list. Remember, it's an immutable list. You can't change it. And convert it to a mutable array. So an array where I can swap everything around. And I want it to belong to the region RC. Then sort it in an imperative way. The exclamation mark here just means that actually it's going to be swapping elements around. And inside this method that I'm not showing, is quick sort, right? Then the array is now sorted, and I return it back as a list. And so this way, I kind of got the benefits of both functional and imperative programming. From the outside, sort is a pure function. Notice there's no effect here. But inside, I just did the thing you would do. I used arrays. And I also get the right performance. If you tried to sort a linked list, a immutable linked list, you couldn't get the n log n complexity you would expect. Okay, another example. This is a stupid example, but just to illustrate a point. Let's say I wanted to add two numbers, and the way I'm going to do it is that I'm going to allocate an array, put them into the array, and then swap the entries in the array, and then pull them out and add them. Obviously, there's no reason to do any of this, but just for the purpose of demonstration. So the sum function here is pure. Again, there is no effect. I say here region starts. I want to allocate an array. This is just a syntax for an array of length 2. The first element is x and then y, and it belongs to region RC. Then I'm going to call some swap function that's going to swap the first two entries in an imperative way, so actually changing the array. And at the end, I index them and I add them. So this adds two numbers in a stupid way. So the point is, this is pure. But now you might ask, well, what about the swap function here? What does its signature look like? Because clearly swap can't be pure, right? After all, it's mutating its argument. And so the swap function looks like this. it takes the two indices we're talking about, I and j. Then it takes an array, but notice now that the array carries not only the type of the elements, t, it could be student, it also carries this region that I talked about. And then, due to its implementation, it has an effect in that region. So that we know the swap function touches memory in the region R. That's the main point. Then the implementation is kind of what you expect. I pull out the elements and then I write them back in the opposite order. But the main point I want to make is that the array belongs to a region and the swap function has an effect in that region. Just to give another example, don't worry too much about the code, but for example, if you want to write a ToString, right, very common thing. So I have a list and I want to return as a string representation, right? So maybe you've heard that you shouldn't concatenate strings, right? Concatenating strings is not so good, at least on Java, for example, because concatenating two strings means you have to like copy them. And so if you do that a lot, it's a performance issue. So instead you should use a string builder. Well, what is a string builder? It's really just a temporary object that you use to put some strings into it, and at some point you're done, and you say ToString to the string builder, and then the result comes out as a string. And so it's really a good use case of sort of the idea I'm selling here, right? That we can introduce, I should have called it RC, but anyway, we can introduce a region, I allocate a string builder belonging to that region, I do lots of stuff with it, I'm changing it, whatever, but at the end, a string comes out, the region is over, and the string builder is gone. And so the ToString function remains pure. All right. So the idea here of the region-based memory is that if we take the effect system as I presented in 1, it is not good enough. You can't just have that because you get this future or asynchrony problem where if you touch something that has just a small effect on one array, then you become impure. But then everyone who uses you become impure. Then the whole program becomes impure, and that was not the point. So to recover from that, we need one more new idea, and that is this, that you can say, here I'm going to do a bit of imperative programming. I'm going to allocate sort of a small part of the heap where I can have mutable things. But once the region is over, that thing goes out of scope, and I return a result. And then my function actually is allowed to be pure, as seen from the outside. Right? So really, we can pretend, so now in Flix, you can pretend to be a functional programmer, but every single function you write could in principle, start by saying, here's a region, allocate some mutable hash maps, do some iteration, and then, return some result. So you really get the best of both worlds. You get the performance, you get potentially the more natural style of imperative programming, but from the outside, people can still trust that, given one input, you always give the same output. Okay, so to look at how you program with these things, we're going to look at a case study, how you can express iterators. Now, this is a bit complicated, I must say. So it sort of shows a lot of richness. There might be details that are confusing, but on the other hand, iterators are often hidden from you, and actually towards the end, I'll just say, well, you don't actually implement iterators yourself, right? They're provided by the library. But I wanted to show it because I wanted to show that these ideas can scale to things that are quite complex. Okay, so let's just remind ourselves, like, what is an iterator? Well, in my mind, it's like a mutable data structure that represents a stream of elements. So it's something where you can pull elements out. And part of pulling elements out means that you're changing the iterator, right? Like you're destroying it in some sense, right? You get one element out, and now the iterator has advanced. It's no longer the same iterator. And at some point, the iterator will end, and then it's useless, right? So, but why do we use them? Well, they can be very efficient. They give us an efficient way to iterate through different collections. So what I mean by this is like, you can have an iterator over a set, an iterator over a map, an iterator over something else, but you don't have to care because it's just an iterator. You don't know where it's drawing its data from. So that's why they're useful. Now with iterators, you should keep in mind there are kind of two operations on them. There are what I call terminal, parentheses eager, and what I call non-terminal operations. So eager operations, terminal operations are things that evaluate the full iterator, right? So if you have an iterator of integers and you say sum, like you want to compute the sum, well, that's going to evaluate the complete iterator adding up all the elements. And then hopefully you're done using the iterator. But if you do, for example, filtering, well, a filtering operation is something that's delayed. It's going to happen not now, but a little bit later when people start asking for elements from the iterator. And so this is a rich data structure, and it puts some demands on the effect system that we'll see. So here's the essence of what an iterator is in Flix when you have an effect system. And there are sort of two new things. So the one thing you might have expected is that we need the type of elements. You can have an iterator over students, for example. But we need two more things. We need the effect. So these are effects that are suspended in the iterator. So this is, for example, if you have filtered and you filtered with an impure function. That means that there's an effect waiting there that's going to happen once you apply a terminal operation. And then the other thing is that the iterator needs some mutable memory itself to do its job, because it probably needs to keep track of where it is in the underlying collection. Yeah. But I think the examples here will make that more clear. So just to show, the point I want to make here is that the effect system actually clarifies things for us. Now, understand it's like a new thing, so right now it just looks more cumbersome and something you have to deal with, but it actually clarifies how our code works. So for example, for the sum function, it says, give me an iterator that produces integers with some latent effect, some suspended effect EF, that also uses region R. Then if you call sum, it's going to release the suspended effect, and it's going to change R, potentially. Now, the same thing is true for toList. Exactly the same. We see that the terminal operations release the suspended effects. The same for each. Gets a little bit more complicated here, right? Because for each means like now we are applying a function eagerly to every element, so that function itself could have some effect. But really, all it just says is that now we get the effect that was suspended in the iterator EF1, together with the effect of F, if it has any, and the region R might be touched. Now, on the other hand, the non-terminal operations look different, and this is really the key. So if I have an iterator, and it has suspended effect EF1, I apply a function to it, I'm filtering. That filter function maybe has some effect. Well, you see there's no backslash here. That actually means this filter function is pure because nothing is happening. Rather, it returns a new iterator where the suspended effect is now the original suspended effect from the iterator plus the new suspended effects from the function we're using to filter with. So by looking at these two categories, and the map function is exactly the same. My point is just that you can now see from the signature, once you learn how to read these things, you can see immediately, okay, this operation is happening later, and this operation is happening now. See how I'm doing for time, okay. Yeah, so I'll just go through these examples. Okay, so if I have a set, for example, and I have this region, I allocate an iterator over the set, and I map this function incrementing, and I say to list, well, I get out the list 2, 3, 4. It's not really that surprising. I get an iterator, right? The set is 1, 2, 3. I'm mapping a function that increments the elements, and then I convert the iterator to a list, so I get out a list where the elements are being incremented. Good. Now, the only change I made now is that I added this print line high, right? And that made this thing impure here. And so now the program will print high, 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 and then it will return the same list as before. But behind the scenes, or if you were to hover in VS Code, hover on this, you could see that the iterator returned by map now has this suspended print. Okay, so both the compiler knows this, and you can know this if you, for example, hover over the expressions. All right. For time, I'll skip the next part, just a few slides. Talk about that later. Okay, so I just showed that we can actually express iterators in a language that has a type and effect system, things become a little bit more complicated, but that's actually a good thing because the iterator API forces us to decide, is this effect happening now, or is it happening when the iterator is being spooled through at the end? So now suddenly from the type and effect signatures, we can see, is this a terminal operation or non-terminal operation? We don't need to read the API. The types themselves tells us. Okay. Now the last thing I'll show is another way we can benefit from these effect systems. And it's how library authors and/or the Flix compiler can give us some more performance in certain situations. And so the idea here is a special form of reflection where, all right, okay, so I have some intro first. Okay, so I just want to say first, most languages that you know, right, like Java, JavaScript, C#, all the major languages, they are eager and sequential. So it means, you know, they don't use lazy evaluation, they use eager evaluation, and there's like one thread running. Now, what if you want some lazy or parallel evaluation? Well, in Java, for example, you can reach for the stream API. But even with the stream API, there's this problem of side effects, right? So if you look at the Java stream API, it mentions the word side effect 18 times, and it uses very scary language like that basically says like don't do it, and you know deadlock and race conditions and surprising results and out of order execution and so on. So if you ever use like a Java stream and you added a print, you should be careful. Just that is problematic. All right, okay, so that's what I said. Now the question is, if we have an effect system, can we do better? All right. You know, on the one hand, you know, why do I have to reach for these streams? And on the other hand, you know, how can I know if it's safe to do something in parallel or not, right? You really can't know. So the idea here is that the library author, who presumably has a bit more knowledge about, you know, the data structure you're implementing and so on, they might know when it would be advantageous to do something in a lazy way or to do something in a parallel way. But what they have lacked is the ability to know if it's safe to do so. So even if they know, this operation, I really like to do it in parallel, well, they can't know if they can do that. Then they can only write in the documentation, this runs in parallel, be very careful. Then you get bugs. But what we can do is that we can reflect on the purity of a function argument. So here I have a map function. It's operating on a map. So imagine you have like some, I don't know, again, from the students to grades, and you're applying a function to all the grades. I don't know, maybe you're computing, you know, if the grade is 5, the student has failed. And if it's, you know, 6, the students have passed. So you're trying to transform like a map from students to grades into another map from students to Booleans, let's say. And the key thing here is that we have this type match construct where I can look at f, and then I can ask, actually, does f here, if it's pure, then I'm going to call it g. Don't worry why I rename it. That's not important. I'm going to call it g. And now g, I know it's pure, so I'm going to call this par map, and it's going to, in parallel, reconstruct the map. On the other hand, if there are some side effects, then I don't dare to do anything in parallel. I could be changing the meaning of the program. So just to give you a small example here, here I create some keys. I just, you know, keys from 1 to 1,000, some values 1 to 1,000, and I turn them into a map. So now I have a very boring map. It just maps 1 to 1, 2 to 2, 3 to 3, and so on. And then I change the map by saying I want to increment all the values. But incrementing them, I'm also going to print them. And because I'm printing, right, that's a side effect. I have to be very careful, so we shouldn't do anything in parallel. So if you run this program, it will dutifully print 1, 2, 3, and then return the updated map. And very importantly, the prints, you see them in order, left to right, following the order of the map, and they could never be happening in parallel. So like imagine you're printing multiple lines and suddenly the output would be interleaved. That cannot happen. On the other hand, exact same program, but if I didn't have the print, it was pure, well, it still returns the same map, but now internally, it's going to spawn a number of threads equal to the number of cores, and it's just going to rebuild the map in parallel. So you get parallelism for free. You as the user didn't have to do anything. So now you can ask yourself, right, in all the code you've written, how many places could there have been some parallelism, but you didn't reach for it because you were not sure it was safe, you didn't want all the ceremony of introducing like a stream and a parallel stream and then doing all that stuff. There's probably lots of performance left on the table here and there, but it would be too much effort to get it. But with purity reflection, we can have the library authors make this decision, and then they can safely enable, for example, a bit of parallel evaluation when needed. Okay, we can do the same for laziness. I'm going to skip that. But just to summarize this one, we have kind of a fresh take on data structure transformations. So if we consider these operations like map and filter and so on, if you give pure function arguments, then we should enable lazy or parallel evaluation, or both. Sometimes we can even, depending on exactly the sequence of operations, do things. Otherwise, if there's something that's impure, then we behave as normal, because that way your program has the exact behavior you would expect. You see everything in order, there are no race conditions or anything like this. Okay, so I pretty much already said this. So I just want to say, in the Flix standard library today, this is already the case. So for example, you have the simplest example, if you have a set and you say count to it, well, if you're counting with a simple predicate, and you almost always are, you don't write a very complex function, it's just, just filtering with some simple pure function, then we will evaluate that in parallel. But if you pass some impure function, we will evaluate it sequentially, preserving the order of effects. We also have some specific data structures that you can read more about that really try to maximize this idea and take it to its limit. Okay, so that was a very deep dive into, we talked about effect systems, effect polymorphism, regions, and then purity reflection. So for the last few minutes, I'm just going to give you an overview of our implementation, because this is not just a prototype, we're actually trying to build a real language. So what we have is, we have a Visual Studio Code extension, and we've implemented almost all of the API. So we have syntax highlighting, inline diagnostics, you can look up symbols. We have basically all the features that you're used to using. It looks something like this. And it just works out of the box. We're even adding autocomplete, very sophisticated autocomplete, so as you're used to, as you would expect. It's actually really tricky to implement, I can tell you. You have like a partial program filled with errors, and then the user's like, oh, what can I write here? It's difficult, but we're trying. So there's already a really good development story there. There's a website, sort of the front page just gives you like a very brief summary of the new features in the language and gives examples of code. We have a set of design principles, so something other languages seem to be lacking, but actually try to write down what our goals are and what our motivations are. Because we're not claiming like one language is perfect, but rather we're trying to define like this language has these values. And then, if you agree with them, you might be interested in using it. If you disagree with it, well, you'll know the sooner. You don't even have to start using it. You can just read our thoughts. There's also an online playground. It runs on a virtual machine, so please don't mind Bitcoin. We have to pay for it. On the other hand, it would be cool if you write a Bitcoin miner in Flix, so that way I'm conflicted, yeah. There is online documentation. There's actually like 140 pages of online documentation, describes the language and how to get started. There's API documentation like JavaDoc or whatever. I mean, you know how it is. Everything is open source. Apache 2 is developed on GitHub. You can try it out, you can contribute and so on. Yeah, so getting to the end. I put these links here. You can find them when you look at the slides, so I'll not talk about that. Now, I've been talking today, right, but this is actually the product of more than 50 people. I just want to highlight a few. So here are my students, my PhD students. If you could just stand up, wave to the crowd, smile and wave. They'll be here after. You can come talk to them too. Also, thanks to the people who are paying for this. So the Research Fund Denmark, Amazon Science, Direct, Stiebe Foundation. And so in summary, I've talked about Flix. It's a functional, imperative, and logic programming language. We did not talk about the logic part at all, but the point was just at a very high level that you could write a function and do some logic programming inside it. That's a topic for another day. Now, one goal is to have a unique combination of features that other languages do not have. I'm not going to go through them. We talked about these today. And then I just want to say, we think Flix is ready for use, ready for early adopters. I showed you there's a nice Visual Studio Code extension. There's lots of documentation. There's a playground. It's fully open source, and you can go to the website and check it out. That's it. Thank you.